Welcome everyone to Growing 1.2. Our learning target for this lesson is to be able to recognize exponential patterns and be able to write equations for exponential growth relationship. Homework assignment that goes with 1.2 is questions 4 through 11 and 42 and 43. So our problem with 1.2 is we are requesting a reward using exponential functions. Now we have a lot of definitions and things to go through here today. So we'll start right in with when we found the number of ballots after 10, 20, and 40 cuts, we may have multiplied long strings of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, so on and so forth. Well, instead of writing long product strings of the same factor, meaning like 2 times 2 times 2 times 2 times 2, we can use exponential form. And this is one of our vocabulary words today, exponential form, which is a quantity expressed as a number raised to a power. In exponential form, 32 can be written as 2 to the 5th power. Okay, when you have the 5 above, that is 2 to the 5th power. So if you need to pause the video, you can write down the vocabulary so you understand it. So our exponential form, such as 2 to the 5th, we can write 2 times 2 times 2 times 2 times 2 as 2 to the 5th, which, as I've already said, is 2 to the 5th power. In the expression 2 to the 5th, 5 is the exponent and 2 is the base. So as we go back to our vocabulary, base is the number that is raised to a power in an exponential expression. And the expression 3 to the 5th, read 3 to the 5th power, 3 is the base and 5 is the exponent. So when we look at exponent, the small raised number that tells how many times a factor is used. For example, 5 to the 3rd means 5 times 5 times 5. The exponent is 3. Oh, when we evaluate 2 to the 5th, we get 2 to the 5th, 2 times 2 times 2 times 2 equals 32. Well, since there are two ways to write 2 to the 5th, we call 32 the standard form, and 2 times 2 times 2 times 2 the expanded form of 2 to the 5th. Let's see if I have those here. Standard form, the most common way we express quantities. For example, 27 is the standard form of 3 to the 3rd or 3 cubed. Okay. So if we were to grab the number 32, we'll say, and the standard form is going to just be 32. Well, our exponential form, as we're showing here, is 2 with our little 5. You have to excuse some of my handwriting because I'm left-handed but using a right-handed mouse here, so it's could get ugly. So our expanded form is 2 times 2 times 2 times 2 times 2. Okay, 5 times. So those are the different ways that we can write the number 32. Standard form, exponential form, and expanded form. Well, Stella used her calculator in problem 1.1 to compute the number of ballots after 40 cuts. Well, calculators use shorthand for displaying very large numbers, which when we deal with exponents, we're going to wind up getting very large numbers. So the way that you would enter this into your calculator would be 2 and then a caret. Okay, this is known as a caret, and then whatever your exponent is. Well, this time it was 40. It gives us back a number like this that says 1.099511628E12. What on earth? Well, this is what's called scientific notation. So that number that I just talked about means it's that number times 10 to the 12th power, and that is scientific notation. Looking here, this says a short way to write very large or very small numbers. Numbers in scientific notation, if it is of the form a times 10 to the n, where n is an integer and a is greater than or equal to 1 but less than 10. Okay. So we can expand this notation as follows. We have our number that we came up with for 2 to the 40th power, 1.099511628 times 10 to the 12th. And that means that we're taking it times a number 1 plus 12 zeros. Okay, so we take this number times 1 trillion, and we come up with 1,099,511,628,000. Okay, let's look at a little video that might help with understanding scientific notation a little better.
Some numbers are really big, some numbers are really small. I wish there was a way to easily express them all. Hey, I found there's an easy way to show extreme scientific play. Scientific notation does it easily. And now I love science more than I ever did before, can't you see? Express your number so that it's more than 1, but less than 10. Take that number and multiply it by 10 to the proper exponent. 300 in scientific notation is 3 times 10 to the power of 2. 10 to the power of 2 is 100 times 3, that's 300, so there's your proof. Scientific notation uses exponents with the base of 10, so you don't have to write out so many zeros again and again and again. Take a number like 0.0023, plug it into 8 times 10 raised to the power of b, where a equals 2.3 and b is -3. You get 2.3 times 10 raised to the power of -3. Express your number so that it's more than 1, but less than 10. Take that number and multiply it by 10 to the proper exponent. 0.03 in scientific notation is 3 times 10 to the -2. 10 to the -2 is 0.01 times 3, that's 0.03, so yeah, there's your proof. Express your number so that it's more than 1, but less than 10. Take that number and multiply it by 10 to the proper exponent. When you use scientific notation, you become a real hero. What's 5.2? It's not a trick, it's 5.2 times 10 to the power of 0.
All right, so that may or may not help you. We're going to do some examples now so that you get an idea. After we do these examples, you may want to go back and watch that video again, because it might make a little more sense. So we're going to change these numbers up here to scientific notation. Well, we're assuming that this is the number 1,234 and that the decimal is currently here. Well, we know that to change to scientific notation, the number has to be equal to or greater than 1, but less than 10. Okay, so we need to get over to where our number is less than 10. 1,234 is not less than 10. 123.4 also is not less than 10. 12.34 is not less than 10. But 1.234 is. So now our number is going to be 1.234, okay, times 10 to the, we moved it 1, 2, 3 decimal places, or it winds up being 1 times 10 to the power of 3, okay? Now let's take 12.23. 12 is larger than 10, so we need to move our decimal over one spot, and we wind up getting 1.223 times 10 to the first. Okay. What about this one? Well, 0.0003 is less than 1, so it's not greater than or equal to 1, so we need to move our decimal the other way now so that we meet this qualification of being greater than or equal to 1 but less than 10. So we move this, we're going to wind up with 3.0 times, again, sorry for my writing here, I'm writing right-handed when I am a left-handed writer because of my mouse. So 1, 2, 3, 4 spots we moved, and it went to the right, so this is a negative 4. Okay. Now these ones here we want to change to standard notation, so we are going to take our number that we had and move it 1 decimal, 2 decimals, 3 decimals, and 4 decimals, so we wind up with the number 12,000. Over here we have 4.23. I'm just going to write the 4, the 2, and the 3. And we need to move, it's 10 times 10 to the negative third, so we need to move the decimal to the left 3 places. So we move it 1, and then we have a 0, we move it 2, add another 0, we move it 3. So our number is actually 0.00423. Hopefully that helps you. Drop some other numbers, do some other practice. We'll get some here with our problem. So, one day in the ancient kingdom of Monterrey, a peasant saved the life of the king's daughter. The king was so grateful, he told the peasant she could have any reward that she desired. The peasant, the kingdom's chess champion, made an unusual request. So here we are, plan 1, the peasant's plan. This is on page 10 of your textbook. It says, I would like you to place 1 ruba on the first square of my chessboard, 2 rubas on the second square, 4 on the third, 8 on the fourth, and so on. Continue this pattern until you have covered all 64 squares. Well, each square should have twice as many rubas as the previous square. So did the peasant make a wise choice? Explain. So let's look at our problem. On the lab sheet, it will have this table and this graph. So you're going to make a table showing the number of rubas the king will place on squares 1 through 10 of the chessboard. Square 1, 1 ruba. Square 2, 2. So graph the points over here for the number of squares from 1 to 10, and write an equation for the relationship between the number of squares n and the number of rubas r. So just like we did in 1.1, we're going to come up with an equation here in A. Part B, how does the number of rubas change from one square to the next? Find your pattern. And then how does the pattern of change you observed in the table then show up in the graph? How does it show up in your equation? Part C, which squares will have, or which square will have 2 to the 30th power of rubas? Please explain how you came up with that. And what is the first square on which the king will place at least 1,000,000 rubas? How many rubas exactly will be on this square? Then Larissa uses her calculator to compute the number of rubas on a square. When is the first time the answer is displayed in scientific notation? Interesting. So, do parts A, B, and C, and then you'll be ready for homework, which for 1.2 is 4 through 11, 42, and 43. Look forward to seeing you in class and answering your questions. Talk to you later.